Welcome back to week 8 of pre-calculus. Our last topic this week is angles. This begins our journey into trigonometry. So, when we draw angles, we will distinguish between the initial side and the terminal side. We think of the initial side as being fixed. Later on, we will agree to always draw the initial side along the positive direction of the x-axis, and the terminal side is somewhere. It measures the size of the angle. We imagine our angle with the initial side being fixed and the terminal side moving in space or in the plane. We will indicate with an arrow the direction of the angle. Later on, we will agree that angles where the arrow is pointing counterclockwise are positive, and angles where the arrow points in clockwise direction are negative. The measure of an angle is the amount of rotation from the initial side to the terminal side. We will measure angles in degrees and radians. 1 degree is defined as 1 over 360 of a circular rotation. So if we imagine a circle, and if we divide it by 360 equal arcs, all of these arcs are equal here. The measurement of each of these angles will be 1 degree. Degrees are written by this small circle symbol. It's important to remember that when you measure angles in degrees, you always have to include units. If you write 90 without the degree symbol, just 90, it's not 90 degrees. It's an angle of 90 radians, which is something very different from 90 degrees. So remember to always write the degree symbol if you measure angles in degrees. An angle in standard position is an angle introduced to the coordinate plane where the vertex of the angle is at the origin and the initial side extends along the positive direction of the x-axis, like in this picture. As I mentioned, we have positive angles and negative angles. A positive angle is the one measured in counterclockwise direction from the initial side to the terminal side. This angle, for instance, in the picture is positive. But there is an angle with the same initial side and the same terminal side, which is negative. That one will be measured in clockwise direction. So in general, the initial side and terminal side don't determine the angle uniquely. Later on, that'll play a major role in our discussions. There are multiple angles with the same initial side and terminal side. There are special angles called quadrantal angles. Again, if we introduce the coordinate system and draw angles in standard position which measure to 0 degrees, 90 degrees, 180 degrees, or 270 degrees. These are very special angles. We will call them quadrantal. Note that these are all positive angles. All four of these angles are positive. All right, so we said already that aside from degrees, we also measure angles in radians. So let's talk about what radians are. So people agreed for some reason to divide the circumference of a circle into 360 equal parts, and the measurement of every such part, every such angle is called 1 degree. There's nothing natural about this process. There's a much more natural way to measure angles, and this way is the following. I'm sure you know from your previous math courses that the circumference, the length of the arc that corresponds to the full rotation, equals radius times 2 times the special number called pi, 2 pi r. Because of that, it seems very natural to divide the circumference of a circle into 2 pi equal parts. When you divide the circumference of a circle 2 pi r into 2 pi equal parts, you will get that each part, each arc, has length r. Each of these arcs, when you divide the circumference of the entire circle by 2 pi parts, each of these arcs will have the same length as the radius of the circle. We declare an angle that corresponds to the arc whose length equals the radius of the circle to be 1 radian. So here, this is the radius of this circle, and this is the radius of this circle. And we start from this point and keep on going until the distance we've traveled along the rim of the circle, becomes equal to this distance. So this distance equals the distance traveled along the circle. When this happens, we declare this angle 1 radian. So one more time, let's write this down. We divide the circumference of 2 pi r into 2 pi equal parts. Naturally, when we do this, each part will have length r, since 2 pi r over 2 pi equals r, each of the obtained arcs will have length r. The radius of the circle in question. And so we say that the angle subtended by an arc whose length equals the radius of the circle is defined as 1 radian. It's a very natural way to measure angles. Much more natural than dividing the circle into 360 parts. Rather, in any circle of any radius, not necessarily 1, take any circle of radius r, pick a point on the circle, join that point with the center of the circle. Take this radius as your initial side. Start measuring angles from this initial side. How do we measure angles? We measure them by the distance traveled along the circle. Different angles result in different distances traveled. As soon as you travel the distance which is equal to the radius, as soon as this arc has length the same as the radius of the circle, we declare the corresponding angle to be 1 radian. That is the definition here. This definition immediately gives us the relation between radians and degrees, because 360 degrees equals full revolution. On the other hand, how many radians is 1 revolution? Well, 1 radian corresponds to the arc of degree r. The arc that corresponds to the entire revolution is an arc of length 2 pi r. Therefore, the entire revolution corresponds to an angle of 2 pi. Correct? Again, 1 radian is defined as an angle subtending an arc of length r. The entire circumference is 2 pi r, but the entire circumference is subtended by the entire revolution. So that must be an angle of 2 pi. An arc of length r is 1 radian, an arc of length 2 pi r is 2 pi radian. So full revolution is 2 pi radians. And immediately from this, if we divide this equality by 360, we get that 1 degree equals 2 pi over 80 radians. In other words, 1 degree is, 2 pi over 360 radians. In other words, 1 degree is, upon cancellation by 2, pi over 180 radian. Likewise, if we want to express radians through degrees, we can take this equality again and divide both sides by 2 pi rather than by 360. That'll give us that 1 radian equals 360 over 2 pi degrees. Upon the cancellation by 2, we get 180 over pi degrees. That actually is roughly 57 degrees. So 1 radian is roughly 57 degrees. It's also important to note here that when you measure angles in degrees, you have to include units. But when you measure angles in radians, you get a measurement that's unitless. Radian measure is unitless. You don't have to write rad every time. It's actually unitless. That is because when you have an angle of 2 pi radians, for instance, it's the quotient of the circumference 2 pi r and radius r, which are both measured in units of length, right? So when you write that 2 pi equals 2 pi r over r, that's circumference over radius. Both are measured in units of length, say in inches. When you divide inches by inches, you get a unitless measure. That is why if you write that some angle measures to 90 without writing 90 degrees, that actually means by default that since you're not explicitly given units, 90 means 90 radians. And that's definitely not the same as 90 degrees. 90 radians and 90 degrees are different angles. So once again, 1 radian is the central angle whose vertex is at the origin, where we have a unit circle, not necessarily unit circle, a circle of radius r, centered at the origin, such that the length of the arc subtended by this angle equals the radius of the circle. That is 1 radian. So an angle of 1 radian subtends an arc of length r. The central angle of theta radians will subtend the arc of length r theta. For instance, this here is the angle of 2 radians, roughly 114 degrees, much like this here is roughly 57 degrees. The arc subtended by this angle is twice the radius. The length of this arc is twice the radius. In this picture on the right, we have different angles measured in radians. This here is 1 radian, roughly 57 degrees. This here is 2 radians, roughly 114 degrees. This here is roughly 3 radians, and you can compute how many degrees that is by multiplying 3 by 57. So that is roughly 57 by 3, which is 150 plus 21, roughly 171 degrees. Now, because a full revolution has a measure of 2 pi radians, half revolution has a measure of pi radians. So this here, half revolution, 180 degrees, is pi radians. Therefore, when you, for instance, add pi to 1, it'll take an angle of 1 radian and move it to a point on the circle, diametrically opposite to the point corresponding to 1 radian. These 2 points are diametrically opposite. Much like these 2 points, 2 and 2 plus pi are diametrically opposite. This angle here is 180 of pi. And much like these 2 points, 3 and 3 plus pi are diametrically opposite. That is because this angle is 180 of pi radians. 180 degrees of pi radians. And again, a full revolution is an angle of 2 pi radians. From these formulas we obtained above, expressing 1 degree in radians and 1 radian in degrees, it's easy to obtain formulas expressing x radians in degrees and x degrees in radians. If I multiply each side of this formula by x, I will get that x degrees equals x times pi over 80 radians. And if I multiply this other formula by x, I get that x radians is x times 180 degrees over pi. Or rather, let's multiply, to avoid confusion, let's multiply in the second formula by y. Y radians is y times 180 degrees over pi. That is the formulas that you have here. You don't have to memorize them, and I urge you not to memorize them, because all you really need to know is that a full revolution is, on the one hand, 360 degrees, and on the other hand, 2 pi radians. From that simple fact, these formulas are easy to derive, all 4 of them. So no need to memorize them. On the next page, we have 2 circles showing common values of measurements of angles, both in degrees and in radians. Angles 45 degrees, 135 degrees, 225 degrees, and 315 degrees, as well as their corresponding radian measures: pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4, have a clear geometric meaning. The points on the circle, which correspond to these angles, split the arcs in corresponding quadrants in half. For instance, the point corresponding to the angle of 45 degrees split this arc in the first quadrant by half. This distance is equal to this distance. Much like this distance is equal to this distance. Now this distance is equal to this distance, and this distance is equal to this distance. Later on, we will discuss geometric meanings of other angles, such as, for instance, 30 degrees. When we get to right angle trigonometry, we will, for instance, say that in a right triangle, the leg that is opposite to an angle of 30 degrees, which is pi over 6, this leg, is half the length of the hypotenuse. If A is a leg opposite an angle measuring 30 degrees or pi over 6 radians, then the leg A is half the hypotenuse C in the same triangle. But for now, let's look at these 3 examples where we need to convert from radian measure to degree measure or vice versa. In this example, for instance, we need to find the radian measure of 1/3 of a full rotation. Well, because a full rotation has measure of 2 pi radians, 1/3 of a full rotation. Has measure 2 pi over 3, 1/3 of 2 pi. Now, in the next example, we need to convert radian measures of these two angles, pi over 6 and 3 radians, into degrees. So, for instance, pi over 6. If we write it as pi over 6 times 1 radian, and recall that 1 radian is 100 degrees over pi, 1 radian is 180 over pi degrees. Now the pi's cancel, and we get 100 over 60 over 6, that is 30. And so pi over 6 is indeed 30 degrees. The other angle, 3 radians, is dealt with the same way. So 3 radians is 3 times 1 radian. 1 radian is 180 over pi degrees. And so that is simply 540 over pi degrees. Well, that is some angle measured in degrees. Because pi is greater than 3, this angle is less than 180 degrees. Probably in quadrant 2. That's about as much as we can say now. 3 radians is, oh, we know 3 radians is roughly 171 degrees. So we actually know that. Roughly 171 degrees. Now, in the next example, we need to do the opposite thing. We need to convert degrees into radians. So, for instance, 15 degrees is easy to convert to radians because we recall that 1 degree is pi over 180 degrees. Correct? I shouldn't write degrees here. It's a mistake. And when you cancel by 15, 180 by 15 is 12, I believe. 15 by 12 is 150 plus 15 by 2 is 30, so that's 180. When you cancel by 15, you get 12. So that is pi over 12. And you can omit the word radian here. And likewise, 126 degrees is 126 times pi over 180. And when you cancel, you can definitely cancel by 2. 126 by 2 is 63. 180 by 2 is 90. So it's 63 over 90 times pi radians. You can actually cancel more. You can cancel by 7 or by 9. 63 by 9 is 7. 90 by 9 is 10. So we get 7 over 10 pi radians. Again, radians may be omitted. It's a unitless measure. All right. Now we need to introduce the idea of coterminal angles. What is this? In many applications, it will be convenient for us to always work with angles measuring in degrees to anywhere between 0 and 360. Although, of course, angles could be negative, or they could be positive and greater than 360. That is not convenient. It's much more convenient to measure, to have angles that are always between 0 and 360. So what do we mean by this? We mean, and we saw it on the first page, that when you fix the initial site and you fix the terminal site, multiple angles will correspond to that terminal site. In this picture, for instance, this angle is 140 degrees, and this angle is negative 220 degrees. Yet they correspond to the same initial site and the same terminal site. Definitely there are more angles than these two that correspond to these given initial site and terminal site. For example, I could take an angle of 140 and add an angle of 360 degrees to get the angle of 500 degrees. That is yet another angle, the third angle with the same initial side and terminal side. For many reasons, in many contexts, we will not be interested in the degree measurements of an angle, but rather we will be interested in the point on the point on the circle to which this angle corresponds. From that point of view, all three angles are identical. The angle of 140 degrees, the angle of negative 220 degrees, and the angle of 500 degrees all result in the same point on the circle. So any such two angles that when drawn in standard position have the same terminal site are called coterminal angles. So here we see that the angles of 140 degrees, negative 220 degrees, and 500 degrees are all coterminal. Again, it means that when written in standard position, they have the same initial site and terminal site. 140, negative 220, and 500. It should be immediately clear that any angle has infinitely many coterminal mates, coterminal angles. Take any angle you want, add 360 to it, another 360, another 360. Each time you get a different coterminal angle, or subtract 360 one time, subtract 360 another time, subtract 360 a third time, and so on. And again, each time by subtracting 360 degrees, we will obtain an angle that is coterminal with the one that we began with. For instance, an angle of 100 degrees and an angle of 460 degrees are coterminal. Both are coterminal with the angle of negative 260 degrees. An interesting question arises. When are two angles given by their degree measurement coterminal? When are two angles, let's call them alpha and beta. It's common to name angles using Greek letters. When are two angles, alpha and beta, given by their degree measurements? Coterminal. If you think about it, the answer is very simple. In order for two angles to be coterminal, it's necessary and sufficient that they differ by a whole number of revolutions. One angle should be obtainable from the other angle by a whole integer number of full revolutions, and a full revolution is an angle measured in 360 degrees. So two angles are coterminal if and only if they differ by a integer multiple of 360 degrees. Alpha and beta are coterminal if and only if the difference alpha minus beta or beta minus alpha, that doesn't matter, is an integer multiple of 360 degrees. Naturally, you can state the same criterion for angles measured in radians. If alpha and beta are two angles measured in radians, they're coterminal if and only if the difference alpha minus beta is an integer multiple of 2 pi. Note, for instance, here that 100 and 460 are coterminal because the difference 100 minus 460 is negative 1 times 360. It's an integer multiple of 360. Negative 260 and 460 are coterminal because, again, negative 260 minus 460 is negative 720, and that's negative 2 times 360, which is also an integer multiple of 360 degrees. So a very simple criterion. If and only if the difference is an integer multiple of 360 degrees if you're measuring in degrees, or an integer multiple of 2 pi if you're measuring in radians. Let's practice finding coterminal angles. In this example, for instance, we need to find an angle coterminal with the angle measuring 800 degrees such that it lies between 0 and 360. The idea in all these problems is the same. If you're measuring angles in degrees, you need to divide whatever your angle is by 360 with remainder. And if you're measuring in radians, you need to divide your angle by 2 pi with remainder. Let me remind you that when you divide integers with remainder, a, for instance, is the dividend, the integer being divided. B is the divisor, the one by which we divide, so B has to be non-zero. For any such A and B, there exist unique integers Q quotient and R remainder uniqueness is important, such that A equals QB plus R, and unfortunately some people end here, and if you end it here, the statement is incorrect. Definitely such Q and R exist, but they need not be unique. The uniqueness comes when you require that remainder R be non-negative and strictly less than the absolute value of B. So in this example, for instance, all we need to do is divide 800 by 360 with remainder. Note that remainder will necessarily be in the desired range, and the remainder will be the angle coterminal with 800. Let's divide and explain why. So of course, when we divide 800 by 360, the quotient is 2, and the remainder is 80. And so if you geometrically visualize this, what we have here is the following. The angle of 800 degrees can be obtained by two full rotations. One rotation, that's 360. Two rotations, that's 720, excuse me, plus 80 degrees more. Two full rotations, that's 720 degrees, plus 80 degrees more. That is indeed the angle that we want, because it's coterminal with 800 degrees, and it's in the desired range, 0 to 360. The second problem here, in which we need to find the angle coterminal with negative 45 degrees, within the range from 0 to 360, can be solved in exactly the same way. All we need to do is divide negative 45 degrees by 340 degrees, 360 degrees, I'm sorry, with remainder. And when you do the division, negative 45 degrees is, so how do we do the division? Given that remainder must always be positive. Well, when you do the division, you find that this is negative 1 as quotient times 360. So negative 1 here is the quotient. And the remainder is therefore 300 minus 40, 360 minus 45, that's 315. That is the remainder. So this angle here is negative 45 degrees, and this angle here is 315 degrees. Indeed, they're coterminal, and this alpha measuring 315 degrees is in the range from 0 to 360. All right. In the next problem, we are given an angle of 19 pi over 4, and we need to find an angle beta that is coterminal with the angle 19 pi over 4 and is in the range from 0 to 2 pi. Well, what can we do here? if we divide this number 19 by 4 with remainder, it will be 19 equals quotient 4 times divisor 4 plus remainder 3. And therefore, I can write 19 pi over 4 as 4 times 4 plus 3 over 4 times pi. When I divide 4 times 4 over 4, I of course get 4. Then I divide 3 over 4. Times pi. And of course this is 4 pi plus 3/4 pi. Now 4 pi simply is 2 times 2 pi. I'm now dividing by 2 pi. That's 2 full revolutions plus 3/4 pi. So on the circle, this corresponds to 2 full revolutions. And 3/4 of a half revolution. Because pi is half revolution, we need 3/4. So we end up here at the point which is the midpoint of this arc. And the angle is this. 1, 2, 3. 19 pi over 4. So we are looking for the coterminal angle beta, which is in the range 0 to pi. So clearly the angle beta we're looking for is simply 3 pi over 4. It is certainly in the range 0 to pi, and it is indeed coterminal with the given angle, 19 pi over 4. By the way, we could divide this number 19 pi over 4 immediately by 2 pi with remainder. Right? If we divide 19 pi over 4 by 2 pi, so we have 19 pi over 4 over 2 pi, pi's cancel, we get 19 over 8, that is, oh, maybe I shouldn't do this. Anyway, we have already obtained what we wanted, so let's not overcomplicate things. Right, we have expressed 19 pi over 4 . We found the angle coterminal to 19 pi over 4 in the range 0 to pi. The idea of coterminal angle brings us to the idea of a reference angle. So for every angle, it's always possible to find the smallest positive acute angle formed by the terminal side of the given angle and the horizontal axis. For many reasons, reference angle for us will be important. For instance, when your angle is itself in the first quadrant, when t is in the interval 0 pi over 2, its reference angle is itself. When t is between pi over 2 and pi, let's make here the strict inequality. When t is between pi over 2 and pi, so it's in the second quadrant, its reference angle is this one. I believe in the picture, the arrow must be not in that direction, but in that direction. This is the reference angle. Of course, that reference angle is simply pi, half revolution, minus angle t. Now, when you're in the third quadrant, so your angle t is between pi and 3 pi over 2, the reference angle, again, the smallest positive acute angle between the terminal side and the x-axis, is this one. This time the arrow is correct. And that angle is t minus half revolution, t minus pi. Finally, when your angle is in quadrant 4, so t is from 3 pi over 2 to 2 pi, like in this picture, this is t. Again, I believe the arrow is drawn in the picture incorrectly. The arrow must be in that direction because the angle must be positive, so the arrow must be pointing in counterclockwise direction. So this reference angle t prime is full revolution 2 pi minus the angle t, so 2 pi minus t. Why are reference angles important? They will be important when we get to trigonometric functions, sine and cosine, and various identities involving sine and cosine. For instance, here, when we introduce cosine as the x-coordinate of a point on the unit circle and say that the coordinates of this point are cosine t and sine t. X is cosine t, y is sine t. Rather, t corresponds to this point. By symmetry, we will argue that the coordinates of this point are negative x comma y, which is cosine and sine of this angle. Well, because this angle is t, this angle is pi minus t. This angle, being the same as this angle, is also pi minus t. Now, it is an isosceles triangle. Two sides are equal to the radius of the circle, which we assume is 1 in this discussion. Implies that this angle is also pi minus t. Therefore, this distance equals this distance. And likewise, this angle is also pi minus t. So the coordinates of this point are cosine pi minus t, sine pi minus t. And we get immediately from this that cosine t and cosine pi minus t are only different by a sign. You can ignore this if you don't know yet what sine and cosine are. We'll talk about this later. And that sine t equals sine of pi minus t. I'm just explaining why we need reference angles. Reference angles are extremely useful when it comes to trigonometric identities like this. We will deal with numerous dozens of trigonometric identities, and they're a lot easier to memorize if you memorize them once for reference angles and then just figure out how to use them when your angle is outside the range 0, 360. For every angle from 0 to 360, we can find a reference angle. And for every angle outside 0, 360, we can find an angle coterminal to our angle in the range 0, 360. And once you are between 0 and 360, you can find the reference angle. And when it comes to trigonometric functions and identities, you will only need to memorize the values of trigonometric functions, sine and cosine, for the angles in the first quadrant. Because the values of sine and cosine in quadrants other than the first quadrant could be understood with simple geometry. But that's coming in the future. So let's move on. Let's talk about areas of sectors. A sector is a shape enclosed by two radii of a circle And the question that often arises in applications is how do we compute the area of a sector when we know the central angle subtending the sector? Well, because the area of the entire disk subtended by an angle of 2 pi is pi radius squared, that we know, right? The area of a disk of radius r is pi radius squared, and the entire disk is subtended by an angle measuring 2 pi. The angle measuring theta radians will be theta divided by 2 pi times pi r squared, which is of course simply 1/2 theta radius squared. A simple formula. Central angle is 2 pi, area is pi radius squared, central angle is theta. It is perhaps easier if we first explain with 1 radian. So 2 pi radians gives the area pi radius squared. 1 radian gives the area pi radius squared over 2 pi, which is 1/2 radius squared. Now theta radians results in an area this times theta, 1/2 theta radius squared. This formula is written here. Here is one simple question. An automatic lawn sprinkler sprays a distance of 20 feet while rotating 30 degrees. What is the area of the sector of grass that this sprinkler waters? So we simply need to compute the area of this sector. Note that when you use this formula, it's absolutely necessary that the angle be expressed in radians. If you use its degree measure here, it'll be a mistake. So we know the angle of 30 degrees. Measures 2 pi over 6 radians. If you don't remember that, it's easy to obtain this because 1 degree is, what did we have? 1 degree is pi over 180 radians. And so 30 degrees is pi over 180 times 30, or pi over 6 radians. Therefore, the area of this sector equals 1/2 times theta times radius squared, which is 1/2 times pi over 6 times radius squared. So what is this? 20 squared is 400 over 2, that's 200. And we can divide by 2 more. 100 and pi over 3, and never forget the units. We are computing the area. Distances are measured in feet. So the area is measured in square feet. All right, and what's left to talk about here in this topic is also circular motion. What's a circular motion? Circular motion is when a point moves along a circle. There are two types of speed that you can talk about when you talk about circular motion. So a point may have a linear speed, which is determined simply as the distance traveled along the circle over time that it took the point to travel that distance. For instance, if the point traveled distance s over time t, the linear speed is of course s divided by t. But there is another type of speed that you can talk about in this context. There is something called angular speed. What is this? The angular speed is the speed measuring how fast the radius of the circle joining the center and the point in question sweeps out the disk. Say the point started moving from this location, and over time t, it moved to this location. Angular speed, commonly denoted by the Greek letter omega, is the angle between these two radii divided by the time it took the point to move from this location to this location. Note immediately that because the angle is measured in radians, and radians is considered as a unitless measure, angular speed is measured in seconds to the power -1. Either in radians per second, or you can simply say in seconds to the power -1. Again, angular speed measures how fast this angle is changing over time as this point moves along the circle. There's a clear relationship between linear speed and angular speed. Linear speed is distance traveled along the rim of the disk, along the circle. Over time that it took the point to move. Now, in its turn, the distance traveled is the length of this arc. Well, this arc is subtended by an angle measuring to theta radians. So S is r times theta. We know that. Length of the arc equals radius times the measurement of the angle subtending the arc in radians. This is how radians were defined. Remember, 1 radian was defined as the central angle subtending an arc of radius of length r, the same as the radius of the circle. That's 1 radian. If I want my angle to subtend an arc of, if I take an angle measuring theta radians, the length of the arc that this angle theta subtends will be theta times the length of the arc subtended by 1 radian, which is r. So the length of this arc is theta times r. Provided, of course, that theta is measured in radians. I recommend that unless required by the problem, you measure all your angles in radians. So here we have our length S as r times theta. Well, from this formula, theta is omega times t. So I replace theta by omega times t. Now the t's cancel. And we get r times omega. And that is the relationship between the two types of speed. Linear speed is radius times angular speed. Angular speed could be measured along with, aside from seconds to the -1. Angular speed could be also be measured in rotations per second or revolutions per minute or degrees per hour. All these units are translatable between each other, as we will demonstrate in these two problems. In the first of these two problems, we need to translate, we need to find the angular speed in radians per second when a whirl wheel completes one rotation every 5 seconds. Well, one rotation corresponds to a radian measure of 2 pi, and one rotation every 5 seconds simply is the angular speed of 2 pi over 5 radians per second. Or if you wanted to express this in degrees per second, for instance, because 2 pi is 360 degrees. That would simply be 75 degrees per second. Every second, we sweep an angle of 72 degrees. All right, in the second problem here, we are given that the wheel of a bicycle has diameter 28 inches, which immediately implies that radius is 14 inches. It's also known that the wheels are rotating 180 revolutions per minute. We need to find the speed of the bicycle as it travels down the road and express it in miles per hour. Well, of course, we're going to use the formula we just derived. So linear speed v of the bicycle equals radius of its wheel times the angular speed of its wheels. Now, the radius of the wheel is 14 inches. What about the angular speed? Well, angular speed, omega, is 180 revolutions per minute, which is not very convenient to work with, but we can always translate this to radians per minute or per another unit of time. One revolution is 2 pi radians. And so that is 360 pi radians over minute. Radians can be a minute. So here, instead of omega, I can write 360 pi over minute. Note that we do get linear speed because the units of this number are units of distance, inches, over units of time, minutes. So it is indeed units of speed. That is a good indication that we are on the right track. Always check that your work results in appropriate units, in the units that you intend to obtain. What's left to do is translate inches to miles and minutes to hours. Well, we have 14 times 360 pi. Every 1 inch is 1/12 of a foot, and every 1 minute is 1/60 of an hour. So when you do the algebra here, you get 14 times 360, 1/12 over 1/60 simply is 60/12, which is 5. When you flip the fractions, 60/12 feet per hour. And now we need to translate feet into miles. This is 5, and 5 times 14 is 70. 70 times 360 pi times feet per hour. And there are 5,280 feet in every mile, so every foot is 1 over 5,280 miles. When you do the algebra here, I believe you get roughly 15 miles per hour. The units here stay. All right, that finishes this first topic in trigonometry. It will be a long journey. We will continue our study of trigonometry next week. Thank you.